Good day, everyone. It's 11:03, so I think it's probably about time to hear. If someone could give me a wave just to make sure that they can hear my microphone. Awesome. Thank you very much for the thumbs up. My name is Lance Cizik, and I'm the Western Regional Sales Manager for HORIBA Process in Environmental. I'd like to thank everyone for joining today for our Raman webinar. Sorry about that. I'm going to speak very briefly here just about some of who HORIBA is and some of our HORIBA products that we have. This will be very brief, but I'm going to talk a bit about who HORIBA is, some of our products, our Raman analyzer. Having a difficult time with that today for some reason, but then as well as some of our other products that the IPE group offers. And once I'm through with that, I'll pass it over to Dr. Dakota Morales, and he'll be able to dive deeper into the Raman and some of its capabilities. We also will have a question and answer session. So what I would like to recommend is that if you do come up with a question throughout the course of the presentation, to please enter it into the chat. Stevie Lee will be moderating that, and once we've completed with Dakota's presentation, we will follow up on those questions. If you have a question after the fact, there will be a follow-up email that's going to be sent out by Stevie and Lupita, which will summarize what we're doing here today. And if you have any questions after the fact, there will be email links in that email for you to send them to either me or Dakota or to Stevie directly, and we will be able to respond at that point. Okay? So with that said, I'm going to move on to a bit about who is HORIBA. Well, we're a multifaceted company that we're based in Kyoto, Japan. We've been around since 1953. We are a family-owned company, which is kind of a fun way to go about. We have a very family-style organization, I guess would be the best way to put it. We have more than 8,200. That number is probably a bit low at this point, but we were incorporated here in the USA in 1973. We have multiple facets. As I mentioned, we have semiconductor, we have the scientific group, we have the IPE group, which is our group, we have automotive, and then we have a medical group as well. So who is HORIBA Instruments? Again, throughout the Americas, in both North and South America, we have over 16 different locations. Specific to the IPE group, we have HORIBA Instruments incorporated in Irvine, California, which is where a lot of our admin is handled. Our financials, all that kind of stuff is run out of Irvine. HORIBA Instruments Incorporated in Houston is kind of the focus for IPE as far as our manufacturing, our service depot, and as well as any repairs for that matter that can't be handled in the field. Things get shipped back to Houston and things get adjusted there. And then we have HORIBA Process Instruments, which is the Raman group, which is based in Salt Lake City. So we have a multiple headed approach as far as how we attack being able to serve our customers. The IPE group, our main products, we do ambient air monitoring, we do combustion control monitoring, process gas analyzers, including our portable PG300. We do systems integration that is not only relegated to HORIBA products, but we have a multifaceted group that is able to integrate multiple vendors into shelters, into racks. We have a full integration house in the Houston area. So if you ever come across anything that you may need as far as something to be built that you might not think HORIBA might be able to do, I would encourage you to reach out to us. More than likely, we've built something that would be similar to what you're looking for. We offer field services as well, field service, and then obviously we have the Raman group, which we integrated into the IPE group 2 years ago, October. So we're very happy to be working with them. Specifically, what you guys are interested in today is the Raman analyzer. It's been around for a while. We do have both a process and a laboratory version. There is a multi-channel process analyzer. There is a single, a dual point. There is an 8-channel, and there is a 16. I'm sorry. There's a 9-channel, and there's an 18-channel version as well. We have no interferences from water or particles, gas bubble, or process temperature changes outside of the obvious dramatic spike or something like that, which pretty much anybody would have to deal with. We use fiber optic coupled fiber optic for our sample line, as far as getting the signal back from the stream or the flow cell back to the analyzer for processing. We do offer a purged Raman enclosure as well, so we can put this in a class 1 div 2 environment, whether that's a Z purge or an X purge, whatever your safety group demands. There's an ATEX Zone 0 certified option as well. It is an IECEX certified analyzer system, and we have, as you can see globally, we have a pretty significant amount of process streams which have been to which the Raman has been installed in. So we have a lot of diversity. We have a lot of applications that we've worked with. We have a lot of flexibility. All the Raman analyzer is it was designed, built, and now manufactured in the Salt Lake City area. Everything down to the lasers is built in-house. So we have solid control over the development of the analyzer, over the expansion of the analyzer, and the improvements on the analyzer. As far as your HORIBA contacts, I'll just give this kind of a breakdown right here. Kevin Fouché is our Vice President and General Manager. Brian Ross is our Inside Sales Manager and Compliance Office. Harsh Agrawal is our Product Specialist for Gas Analyzers. Giancarlo Aguirre is our Salt Lake City Operations Manager, specifically for the Raman. Dr. Dakota Morales, who you will hear from in just a few short minutes, is our Process Raman Product Specialist. You have his email there. And again, all of this information will be supplied once after the webinar is concluded. We'll wrap it up for everybody. So, and then there's Mick Dolenmayer, who is my counterpart on the eastern side. There's obviously me, the Western Regional Sales Manager, and then there's Samuel Francois, who covers some of our water products, TOC analyzers. Some of you may be familiar with the L'Aqua Twin, but this is kind of the heart and soul of the IPE group that we have here. So I would encourage you as well to go onto some of our social media platforms on YouTube, Instagram, Facebook, TikTok, also LinkedIn. There are past webinars that we've done. There are some how-to videos that are on there, and we're constantly looking to expand on our content. So if you have any suggestions, or if you have any content that you'd like to see from HORIBA, we do encourage you to reach out to us. The only way we know what our customers want is by them telling us. So we want we want feedback, we want information from our customers and our potential customers as well. So with that being said, I thank you for your time, and I will pass it over to Dr. Dakota Morales, who will talk a bit more about the Raman.
All right, thank you very much, Lance. If I could do the same thing and get a thumbs up that you guys can hear my microphone okay? Okay, great. Thank you so much. Yeah, thank you, Lance, very much for that introduction. I'm very happy to be able to start this presentation and this webinar on acid gas loading. This is a very unique application that Process Raman will have a very high aptitude at doing successfully, and we are very excited about the opportunity to show you guys this today. So as soon as... Hey, Stevie, it's asking me to tell you to make me the presenter on here. Thank you. All right, let's get into it. All right. Okay. All right. Thank you guys again very much. So yeah, today, as Lance said, we are going to talk about acid gas loading in immune systems. Definitely not in a purely, academic way. The goal really for today is to be able to connect loading to process Raman to what you actually deal with in the field at your refinery. Things like unit stability, troubleshooting speeds, energy uses, treating margins, things like that can all be you know, overseen with our process Raman technology. So, as we go along through this, I'll definitely be circling back to one theme over and over again, which you guys will see very quickly, which is that, with our process Raman, the idea is that you should be able to see your solvent condition in real time, and you can manage that by the feedback with our Raman analyzers here. So let's anchor the definition first of acid gas loading, right? Because everything is going to build on this. So acid gas loading is just very simply the amount of CO2 and H2S that the circulating solvent is carrying at that moment. So essentially, operationally, that matters because loading tells you two things that you're always trying to understand. One is how much capacity the lean amine has left when it comes back, or sorry, when it returns to the absorber, and how much captured duty the absorber is actually delivering, as reflected in the rich amine leaving the contactor. So this is where it becomes an operator's variable to take care of. So when lean loading creeps up, margin is going to shrink, and units often become more sensitive to feed changes and the hydraulics of the system. So unexpected shifts in rich versus lean loading are also one of the fastest ways to separate absorber side issues from regenerator size issues, which really speeds up the idea of troubleshooting and really nailing down what's going inside of this amine unit. So let's go over some common loading patterns and what they indicate. This should be able to make something practical of the definition of acid gas loading, right? So when refinery or unit operators say loading is a diagnostic, this is what they actually mean, right? So it's not just a number, it's an actual pattern that they're seeing. And these pattern points should be able to describe or at least point to the likely constraint of the amine unit at that time. So we'll start over here on the right side. Let me get my laser pointer. So yeah, so over here on the right side, right, probably the most common loading pattern that we see in these amine units at refineries, right, is that lean loading will obviously start creeping above baseline as time goes on. So when lean loading is elevated, the first assumption is usually regenerator completeness. So either the stripper isn't restoring the solvent as expected, or the solvent itself has completely drifted from heat stable salts, just time degradation or contamination. And all of those, of course, are going to effectively reduce usable capacity. And so what an operator, would typically feel about that is that they're using more steam or more circulation just to keep that treated gas stable. And that's because the unit needs to compensate for reduced solvent effectiveness. Another really common loading pattern is when the rich amine loading increases very abruptly. So in other words, when rich loading jumps, one common driver is just very simply that there's more acid gas coming in, right, to the unit. And so feed souring will then change partial pressure and uptake. And then another factor of this could just basically be improved contacting, where uptake increases because the mass transfer within the unit got better. So either way, this random spike in rich loading rising is going to tell you that the absorber duty has changed, and the operator needs to respond deliberately, and not just blanket, something, basically like throwing all the darts, at the dartboard at the same time. And very lastly, when the treated gas is off spec with no change in the rich loading to begin with. So this is a very, very classic troubleshooting signal in these amine units. So if treated gas deteriorates, but rich loading doesn't move at all, it definitely is suggesting that the absorber isn't contacting effectively at all. So there's some issue, right, with hydraulics or foaming or, something. And what you see operationally is actually very predictable. So the more circulation, anti-foam, there's maybe rising partial pressures, but the improvement is limited because, right, in the unit, we're not actually fixing the core limitation. We're just working around it to get to basically put the treated gas to go back to on spec. And essentially, right, what this means is you can't really control what you can't see. So with that framing, the uncomfortable question really becomes, if loading is supposed to be this powerful diagnostic, then why isn't it treated like a primary online variable in more units in the same way that, we look at online analyzers in blending applications or cuts off of a fractionator, right? Or, side cuts from a crude distillation unit, right? And the short answer really is that today most sites are controlling these critical chemistries inside amine units based on indirect signals. And these indirect signals are gonna only behave when the system stays inside like a very narrow idealized box. So traditional loading measurements, right? We don't directly measure loading online. So we actually will look at bulk property signals today to sort of, get us the idea of what is actually going on inside your amine unit. So this is just going to be a short walk through the table row by row, because each measurement here of these bulk properties of the liquid, they all fail in a different way, and just knowing how or why they're failing, that can save time too. So, right, we'll begin with conductivity. I feel like this is the most common bulk property signal that gets measured in these amine units that I've seen personally. So conductivity is very sensitive and it's very easy to trend. So it does its job very well at measuring overall ion content, but that's all that it's doing. It's just fundamentally only measuring total ionic behavior, and it's not selective to the CO2 or hydrogen sulfide loading at all. And when the conductivity signal is shifting, it could be because the acid gas loading is changing, or it could be other things, right? Like salt buildup, temperature effects, or other ionic species are making their ways in there. So it's very useful as an extremely broad health indicator of the solvent or unit, but it's not a definitive measurement of each of those things at all. Next, typically, is done with a Coriolis meter, so a flow meter with the density output to get a density or specific gravity of the liquid, of the solvent. And, density can move with loading, which is why it's appealing, right? That definitely makes sense just intuitively. But the challenge is that it also moves with amine concentration, water balance, and the same contaminants that I mentioned before. So in a real unit, like in real life, right, where multiple things are varying at once, it becomes a lot harder to argue, that a density change equals a loading change unless you really have a years and years of like qualitative data that that an operator can kind of feel out. Maybe it becomes more of an art than a science when you're using a density meter. Another bulk property signal that gets measured quite often is refractive index with the refractometer. I see this as common as I do with the conductivity probes. And essentially, right, what refractive index is doing, and it's often more aligned with the mean strength, and it is very valuable for that. So there's a lot of ROI for refractometers on, the actual strength of the amine solvent itself, but it's extremely temperature sensitive. Refractive index, is extremely dependent on the temperature of the liquid, and it's definitely not selective either to carbon dioxide or hydrogen sulfide. So it's a solvent concentration tool more than a loading tool. So again, not really, being able to look at acid gas loading directly. And then very lastly, the treated gas analyzers, right? So for an online gas analyzer that's looking at CO2 or hydrogen sulfide, right? We're getting outlet gas composition, and this absolutely matters, but it's still the outcome variable. You're seeing it after the fact, right? So it doesn't directly tell you whether the root cause is the lean solvent quality, absorber contacting, regenerative performance, so on and so forth. Um, and all of these, online gas analyzers, they come with sample conditioning, they come with calibration drift, they come with consumables that cost a lot of money and maintenance and long nights figuring that out, right? So collectively, right, if there's a idealized way to, have all these measurements work together, it's not that they're bad measurements, they're just not direct. And that, distinction is what's going to drive the next couple of slides. So for an actual current modern day online measurement for these sort of issues in acid gas loading, the most chemically direct traditional approach today is online wet chemistry. So these analyzers target things like amine strength, total acids, total alkalinity, etc. And they can provide periodic lean and rich conditions. And keyword there is periodic. So the limitation really is in the operational side. So they're very sensitive to the sample handling itself. So we definitely have to sample condition. We definitely have to cool the sample. Definitely can't put these things through at high pressures. And they require ongoing calibration and maintenance. And they have very costly reagent consumables that get used up very quickly, especially with our online titration systems. And probably worst of all, right, going back to that keyword of periodically, is that the cycle time of these is whole tens of minutes, which means that they're often just reporting what the unit was doing, not what it is doing right now. So wet chem or online titrations can be a very strong periodic reference, but it's still often not fast enough to drive confident real-time control during upsets, or even better, being able to see the predictability of, is an upset coming, are we trending the wrong way? And so right here, right, the value of real-time acid gas loading measurement is, this should be kind of like the pivot point in the story, right? So traditional monitoring can be accurate, but it's very delayed and has limited visibility. So traditional monitoring tells you what happened, but HORIBA process Raman can show you what is happening. And that changes operator behavior, right? So instead of maybe going back to the first couple of slides, instead of correcting broadly, like, let's just increase stripping severity just in case, we can now correctly narrow that down to, okay, well, actually, my Raman analyzer is showing that the lean condition is drifting. So, regeneration needs to be leveled, or rich uptake is collapsing. So maybe the absorber side contacting is an issue. So, being able to actually, look at these things from a practical standpoint, once you have an online measurement that's fast and direct, that actually is an all-in-one measurement analyzer, right? So we're talking the acid gases, the amines, all that stuff can be measured in the same measurement with our process Raman. A few benefits are going to start showing up consistently, right? So you respond faster to feed souring, you reduce default overstripping, you get earlier warning signs of absorber hydraulics, contacting limitations. And the point here, right, isn't necessarily with the process Raman, you get more data. The point really is that the unit stops being driven by delayed confirmation and starts being driven by current conditions, which will completely revamp the way that the operator is handling, and having a whole nother tool and overview of the unit here. So let's translate that into visibility, or that visibility gap into actual cost, right? So when loading isn't directly measured, plants always pay for uncertainty in these four places mainly. So the first of most obvious, is going to be steam management. So without a measured lean condition, operating severity tends to creep upward to protect spec margin. And that's completely understandable, right? It's better to be on the safe side of everything always, even if that means giveaway. But energy becomes the default safety factor always. And so this sort of, pathway to, ROI with real-time monitoring is we're reducing the unnecessary stripping severity by having a much stronger control to the lean condition that the plant wants to be at. Likewise, this is sort of a ramification of the previous point with unused treating capacity, right? So capacity loss often always shows up as higher circulation, right? Being absorber, partial pressure changes, and eventually, right, we get that throughput constraint, which is gonna just, kill that solvent completely, and you got to get it out of there. But the idea is that capacity can degrade gradually, and without this sort of visibility over time, the unit just gets harder to run. So with real-time monitoring, right, your pathway to ROI is pretty straightforward. It's through the throughput that gets unlocked with being able to have, use all of your treating capacity, use the amine solvent the way that it should be, and then when you're doing that correctly, you are avoiding, overstripping on your steam management side. So you're avoiding more energy costs. So these first two kind of go hand in hand for sure. Likewise with corrosion and fouling, which is very common with any sort of, um, higher acid gas inventory or any higher acid in a plant, right? And these gases are of no exception. So long periods of elevated acid gas inventory can definitely push, corrosion and accelerate exchanger fouling. But visibility here is the prevention tool. So this allows our customers to avoid living in a high risk solvent condition for corrosion and fouling for extended periods. And then very lastly, for labor burdens, right? Manual sampling of, hydrogen sulfide bearing liquids takes time for sure, because you have to handle it, very safely because it carries exposure risk. And when measurement is continuous, sampling actually becomes just targeted and confirmatory. And you sort of are changing your mindset, right? Where if you just know you're targeting a sample, however many times a week, just to confirm that the process ramen is, giving you the results that you want, instead of sampling being the actual primary way that you know what the unit is doing, that completely changes the amount of labor burden on the operators and the engineers that are involved. So the real-time measurements that matter in this application, right? Like we don't need to necessarily boil the ocean or like climb Mount Everest to do this, right? Very straightforwardly, we can just start, in a very simple way of just measuring rich amine coming in and lean amine coming out. And lean is your direct readout of regeneration completeness. It's the solvent restoration, and rich is your direct readout of absorber uptake. And when you trend them together, you can very quickly discriminate between regenerator limited versus absorber limited operation. And that is so crucial. And between true feed souring versus hydraulic contacting degradation. And that's why these two measurements are so operationally powerful. Just, at these 2 points, this opens up, a very large range of, control factors with our process ramen. So let's actually get into what our process ramen is actually measuring now and get into the meat of the expected results, which I'm sure, you guys are probably most interested in anyways. So we'll just get right into it. So here are some process ramen spectra on the right that were collected of different amine solvents with CO2 loaded into them. So, right, with Raman spectroscopy chemically, this works because mixtures of different amines and different CO2 loading states produce very distinct Raman features, which have enough uniqueness to build very stable chemometric models. And, any of these like common solvents that get used in, these amine units at a plant, right? The practical implication is that the measurement strategy of Raman spectroscopy can absolutely be adopted across common amine chemistries and things like bicene too, so different contaminants. So the spectrum slide here is really to make the point very tangible. You're not just getting a single number from a black box of a spectra. or spectrum, you're actually getting a very straightforward chemical fingerprint that contains information about multiple species, right? So in the same way that everyone on this call or in this webinar right now has their own fingerprint that is used to identify like, oh, this is Dakota or that is Lance. All of our amine solvents act the same exact way in Raman spectroscopy, and likewise, so does CO2 and H2S. So that's why in practice, Raman can absolutely both support operational control and the diagnostic part of loading patterns, because when the process changes, then this spectra changes in a way that can be interpreted into the actual components that your plant cares about. So further getting into this with something like heat stable salts, right, with HORIBA process Raman. So these heat stable salts are a major reason why solvent capacity erodes over time. And the key characteristic of this, right, is that these are highly anionic species that do not regenerate in the stripper. So in other words, right, once they are formed, they will always stay in the loop and permanently consume amine capacity until new solvent gets brought in. So monitoring heat stable salts isn't just, nice chemistry or a nice way to see contamination, because it's actually directly tied to capacity management, right, of your amine solvent. So you can reclaim your stripping strategy and then avoid gradual loss of that for, to maximize your treating margins. And because typical, heat stabilized salts, much like amine solvents, have very identifiable spectral signatures, Raman spectroscopy provides a very practical way to trend them online. So, some common HSSs that we see, right, in these units: sulfates, oxalates, acetates, thiosulfates, so on. Here is a spectrum of some anions of the heat stabilized salts showing up in our process Raman spectrum. So you can see very straightforwardly, right, sulfate has its own characteristic peak, thiosulfates have their own. And these, don't overlap. They allow us to really narrow down and get into the guts of the Raman spectra with our resolution. And the pathway to ROI is exactly from that, or for that, for the HSS monitoring. So we can extend solvent life, minimize steam usage from optimized lean loads. So when you can actually monitor these heat stabilized salts directly, these two ROI pathways show up very, very quickly. So expanding on the use case of the idea of heat stabilized salts, right? So we can actually detect these sort of salts like sulfate, for example, at double and single digit ppm. So this sort of, expands the use case beyond loading alone. So in addition to lean and rich loading, right, you can actually build ppm level chemometric models for degradation products like heat stabilized salts. And then you can deploy, these stream specific models where they're needed, depending, where we're measuring or how we're measuring with the process Raman. So, these heat stabilized salts, right? They're important because a lot of these chronic amine problems in plants, right, aren't just from one variable, right? They're all interactive and they all interplay with each other. Solvent condition, contaminants, operating severity, they all feed and influence each other. And being able to, look at something at ppm levels for heat stabilized salts, right, gives you much earlier warning and clearer and cleaner root cause separation for, what's influencing the issues the most. So here we have some actual model results from our process Raman analyzer with a real customer that we built these models for amine degradation in a plant, right? So you can see here, up at the top, we have some of our favorite, heat stabilized salts that they asked us to look at. So we've got some chlorides, thiosulfates, sulfates, sulfide, oxalates, right? All of these models were built with just about 70-ish samples, depending on, some were 70, some were 71, just to do with, outlier detection as we were building the model. But either way, it only required 70 different measurement collections from the end user to build this model for them. And we got some really nice errors here. These are all in ppm for the salts up here. So you can see here, we were well within the accuracy ranges that they, asked us to get. We really only want to provide chemometric models that actually make sense to the user, right? And that's something that's very unique about our process Raman team with HORIBA, is that we do have a dedicated chemometric modeling team that can help build, train, and support your team of chemometric models throughout the entire lifetime of the analyzer. So it's definitely not a situation, right, where we just drop the analyzer off, commission it, shake your hand, and that's it, right? No, we definitely, for all of our process Raman applications, want to empower our customers with these chemometric models and be able to support them, with this process of achieving accurate measurements. So on the bottom part of this table is all of our amine measurements, right? So just to really drive this point home, right, is that this was an all-in-one measurement, right? So the analyzer didn't go through, and do one measurement just for the sodium salt, then on formate, then on chloride, right? No, this was all done within the same 30 seconds to achieve these results. So this sort of introduces this process Raman analyzer as an all-in-one analyzer, being able to do all of these parameter measurements, communicate all of this stuff to your DCS, which then an operator can read out, through an APC, for example, and really have a really nice overview of, their unit here. Here's an individual amine stream model, some modeling results for a DEA stream and a DGA stream with a customer. So again, we only needed about 51 and 35 samples. And you can see here, right, we were measuring total hydrogen, the H2S, formate, CO2, alkalinity, total anions even, the water concentration, the water levels. So these are just very typical measurements and results that we can achieve with our process Raman for these sort of acid gas loading applications. So into the actual product line of the process Raman, right? So here on our left side are our offerings for our online process Raman, and then over here on the right is our QC/QA process Raman. So basically, what you would find in the actual laboratory versus what you would find in the actual field. These measurements were done using these instruments that you see on the slide right now. So these products that you see right here, these are our process Raman offerings, and those are the same analyzers that did the measurements on the few previous slides. So Lance did a really good job going over some of the online stuff already, but just to refresh and reiterate here, for our process Raman analyzer, right, we can do single and dual point measurements are our most basic, option. So something like a dual point measurement system on the rich and lean amine lines would be really, suitable for an application like this. For our customers that want to extend to even more sampling points, we have a fiber multiplexer option, which is this little guy right here sitting in our rack. And that can be extended to a 8 or 17 different sampling points on our 9 or 18 channel multiplexer. And this really allows the online Raman to operate at its best, right, at the apex of operation. So you can look at up to 17 different sampling points with just one analyzer, which is super, great for our customers that want to be able to have flexible installation points or really want a hand or a handle, I should say, on every part of their process that they're interested in. I'll get into the most common sampling option for this application on our next slide here, but I will just talk very briefly about our QC/QA process Raman. So our benchtop laboratory Raman analyzer can be connected or interfaced to a liquid autosampler or an LPG autosampler. For this application, I will, of course, just focus on the liquid autosampler. So this allows for automatic measurements in our software with our process Raman in the lab. So basically, a technician or a lab chemist can come in, load up the liquid autosampler with different amine samples or whatever sample might be there, right? And we can, go through that with the autosampler depending on the, concentrations of the liquid. But regardless, we offer this system to be used in tandem with the online, and they basically kind of synergize together, right? Where when there's an online measurement that's taken, or there needs to be a new model built, for this, you can use the lab analyzer, transfer the model to the online, and so on and so forth. So both of these analyzers work in synergy with each other to give our end users the most control and the best options for using what our process Raman is really good at. So on the online side for our sampling, our flow cell enclosure, right? Our specs here, it's about 20 inches wide, 24 inches high, 7 inches deep. So, just for context, if you're standing in front of it, it's basically the width of your shoulders probably. And the idea here, right, is that it looks very simple on first glance, and that's because it is. With process Raman, we don't need to do any sort of sample conditioning. So we don't need to chill the lines. We don't need to do sample recovery. We don't need to control flow. We don't need to control path length inside the flow cell because we just measure at a stable or at a fixed geometry when we do this. So a lot of the issues that you see with online process GCs or online NIR analyzers with sample conditioning, just very straightforwardly with Raman, we really don't have to consider those to be issues. Process Raman doesn't really fall victim to those sort of things with our samples. So we will just very happily take your sample as is and do all of our spectroscopy that way in just a few seconds. So essentially how the flow cell enclosure works is we flow your sample in and it will go up into this flow cell right here. And this in the bottom right is a cutaway of the Raman probe pushed up against a sealed sapphire window looking into the stream itself. And so this is how we can protect the probe from any upsets in the stream to minimize damage or anything like that. If there were to be overpressurization or temperature fluctuation, it should not theoretically affect the probe in that way behind the sealed sapphire window. So very nicely, as the stream does its sharp right turn here, the probe will send the Raman laser out into the stream and scatter the Raman signal, collect the scattering back into the probe, and then we can bring that light through a fiber optic cable into our analyzer and get the reading. And after that, the flow of the flow cell enclosure just continues through this way through an electronic flow meter that visually and electronically says, what the flow is. And then we just dump it back out into your line, essentially. So we only need to borrow it for a few seconds or borrow your sample for a few seconds, and then we turn it back to you, without invasively sampling, without chemically needing to change anything. We just give it right back to you. So we'll take your sample as is and we'll return it as such. We also offer customized wetted materials. So, depending on the severity of the acid gas or what you're actually looking at, we offer an array of different options for these flow cell enclosures to make sure that these will be okay in the environment that you want them to exist in, as well as they will be okay with the samples that will be flowing through this. So to close, I'm just going to summarize really the core message here, and that is that loading is one of the most informative variables in amine treating, and measuring it directly with Raman in real time completely revolutionizes and changes the speed and confidence of your operator's control and their abilities to troubleshoot. So again, right, you can go to 1 to 17 different sampling points with just one online analyzer. Our detection range is the best in the market right now with single-digit ppm to 100% volume. We have state-of-the-art chemometric modeling support. So this is very unique to HORIBA, where we have teams of people that are dedicated to this service and helping you build your chemometric models. Chemometric models are included with the purchase of the analyzer. So we make sure that you're getting set up correctly and appropriately and that you are good to go. And if that includes, empowering your team to be trained on chemometric models, so you're not just dependent on HORIBA for this sort of support, we also offer that as well. And, a typical installation, right, and commissioning is about 2 days plus 1 or 2 days of on-site training. But, of course, we will not leave until you want us to. And typical maintenance on these guys is about 2 hours per stream per year. And all of this maintenance is just very simply coming from cleaning this flow cell right here. Just this little window of the sapphire window. You can just unscrew this plug, stick a Q-tip into it or a cotton swab, and clean the sapphire window off as, liquids run over it. There's potential for it to foul over, months of use. So basically, this is the only real maintenance because we don't have any consumables. We don't have any moving part replacements in our process Raman analyzer. So maintenance is very low for these sort of applications. So thank you all again very much. I would really like to encourage you all to visit our brand new HORIBA Process Ramen website. We just got finished launching it a couple months ago with brand new content, brand new pictures, brand new spectra. So if you've been to our old ramen website, it definitely does not look like it does now. So we really encourage you to take a look at that. There are contact forms, there are request for quotes, forms on there. But of course, if you'd rather talk to an actual person and get this figured out in real time with us, please feel free to contact myself or Lance. We are focused on the process ramen solutions, and especially with our customers as we turn into the new year, figuring out, what applications and where this process ramen might fit best for our end users. So yeah, please feel free to reach out. And that concludes the actual presentation part of this webinar. So thank you one more time. We will be very happy to go through any questions if anyone in the audience has anything that they would like to go over.
Thank you very much, Dakota. Stevie, I don't see any questions in the chat box or the questions box as well. So I guess with that being said, if there's anyone out there who has any questions once we're over here, as Dakota and I have both mentioned, we are open to answer any of those. We will have our emails sent out to you once this is over. We thank everyone for their time and hope you all have a great day. Bye.
Oh, actually, Lance, we do have some questions coming in.
Okay.
All right. Thank you, Dakota, again for your presentation. I have a few questions here I would like to from our audience. So which laser wavelength do you use for this application and which power? That's the first
Yeah, no,
question.
that's a great question. So to begin, all of the spectra that were collected that was shown in this presentation was collected with a 785 nanometer laser. And our lasers are certified class 3B lasers. So we operate with laser powers at no more than 450 milliwatts for safety reasons. So that is the wavelength and power of the spectra that were collected in here. We are also looking towards going to longer wavelengths for some of those darker amine solutions. But regardless, we've found a lot of success with the 785 nanometer laser.
All right. Thank you. So the next question I have is in reference to earlier area classification for C1D2, what is the ambient temperature requirement? And can the C1D2 enclosure be installed outdoors?
Yes, so all of our equipment can be installed outdoors. So whether that's in the Arctic, of Canada, where we have these, analyzers out in the field, or in the jungles of Vietnam, or in the humidity of Texas, right? These analyzers definitely exist outdoors. So we are very apt at integrating things out in the field for, being exposed to the environments. And in that case, we'd put a purged enclosure over it. So ambient air temperatures, right, are mainly irrelevant. Like I said, we have we have a wide variety of environments that these analyzers sit in, 365 days a year. Because if it's a very humid or a very hot environment, like we see for some of our customers, we can just install vortex coolers and an AC unit. things like that, just to keep temperature stable and comfortable for all the optical components in the analyzer. So anything that you might be worried about in terms of hazardous areas or outdoor installments, I promise you we've seen it already. So we'd be very happy to, to get into to whatever your specific requirements might be. That should be very straightforward to go over.
All right, and I think we have a very good question here. Like you mentioned earlier, Dakota, HORIBA Raman chemometric model, is it transfer from one analyzer to the next, and does the treatment of laser source require model redevelopment?
Yeah, that's a great question. So I'll start with the latter one first because that's easier to or more straightforward to discuss, I should say. And the answer is no. So when we build chemometric models, we normalize the laser power out of it using, sort of a proprietary sort of pre-processing method. So we do not need to, rebuild models every time that, an analyzer needs a laser replaced, which first of all, only really happens every 3 to 4 years is the lifetime of our lasers on our online analyzers. And they come with redundant laser backups. So if one laser were to fail, it'll automatically just kick a redundant laser back on. So you just stay online. And when that happens, we don't need to switch models at all. So laser power or fluctuations in power automatically get accounted for in the way that we build and run our chemometric modeling software. To answer the first part of the question, the former part of the transferability, yes. So we've seen really good transferability with our customers as they build models for their process streams on their lab units or vice versa. We typically would suggest that models that are built online models that are going to be used online should just be used with online spectra. But in situations where that's not possible, or if a sampling point is offline or whatever random situation it might be, we do have really successful transferability references and a really good hand on that, because Raman spectroscopy has really sharp, unique, and defined peaks, which makes peak identification and transferability very straightforward in comparison to, some absorption-based techniques like FTIR, FTNIR, NIR. Raman is scattering, right? So it's a completely different ballpark in the way that we collect these Raman spectra and the way that we model them, and the transferability from unit to unit is also very straightforward. We use the same optical components inside our lab units as we do our online units. And that's done with transferability in mind. So it's the same sort of camera, lenses, grading, all of the actual innards of the analyzers we keep extremely constant, and we match from unit to unit for customer to customer. So we have a really nice handle on the transferability of these models and spectra.
All right, and we have the last question here. Is Raman able to differentiate between carbonate and hydrocarbonate?
Which hydrocarbonates? Like I guess are you asking about bicarbonate?
Yes.
Yes. So if it's molecules that are different from each other, Raman will definitely be able to see the differences in those. They will all have different unique spectral fingerprints. If whoever asked that question, if you want to email Lance and I after the fact, or give us a call, we'd be very happy to do a free demo for you where we can get the use your samples or use our own samples, right, of whatever analytes that you're looking for, and we can run some samples with our analyzers ourselves at the factory, and we can give you some demo spectra of this is what bicarbonate versus bisulfate or bisulfite would look like in a Raman spectrum, for example. So yeah, we'd be very happy to follow up on that and actually show you real data.
All right, sounds good. Thank you so much, Dakota, for answering all those questions. And thank you again, everyone, for your time today. There will be a short survey coming out after this session, and feel free to answer it because we would like to get more input from your end regarding the next webinar session. And thanks again for your time today. Have
All
a
right,
great
thank
day,
you guys.
everyone.
Yeah, thank you guys very much. Appreciate it. Thank you.